Physics. The recent image captured by this telescope has generated compelling arguments that have surprised experts, putting an end to much speculation. The telescope's most recent discovery is visually stunning and could transform our understanding of the universe. The discussion among experts that this image has resolved centers on the perception of the cosmos. The stunning image taken by the James Space Telescope challenges our understanding of the universe. This finding addresses one of the main problems in astrophysics: the age of the universe and its rate of expansion. Scientists of different generations have been puzzled by this unsolved phenomenon and have carried out numerous studies in search of answers. Cosmologists investigate how the world originated, how it works, how it has changed over time, and how it will end. In the last 100 years, great advances have been made in this field. The Big Bang theory, the most widely accepted theory in cosmology, holds that the universe has been expanding for approximately 13.8 billion years, starting from an extremely hot and dense state. The Hubble constant, which indicates the expansion rate of the universe, is used to measure its growth. However, determining how to measure the Hubble constant is not straightforward, and there are two main methods: local measurements and measurements of the early universe. In space, objects such as stars and Type 1a supernovae, which are used as standard candles because of their constant brightness, allow astronomers to measure how far away they are and thus calculate the Hubble constant. As the expansion of the universe varies in speed, scientists can calculate the Hubble constant. There are two main approaches. One is the measurement of the early universe. Scientists use readings of the cosmic microwave background radiation, CMB, discovered in the 1960s as the afterglow of the Big Bang. This microwave energy comes from when the universe was only 380,000 years old. Astronomers can determine the age of the universe and its expansion rate by measuring the tiny ripples of temperature and polarization emitted by the CMB. However, there is a problem. These methods do not yield the same result. Local measurements suggest that the universe is expanding faster than the CMB data indicate. Scientists have been hard at work trying to understand why the results differ. To unravel more mysteries of the universe, more studies are underway. The differences in measurement indicate that we do not yet know all the signs or that there are errors in one or both methodologies. But thanks to the James Webb Space Telescope, we can peer farther into the darkness of space than ever before, revealing elements, planets, and galaxies we never thought possible. Scientists hoped the data found would help them calculate the Hubble constant. But the first wave of data has revealed new things that don't line up with our expectations. Could this information give us a new perspective on space? We may need to rethink what we know about how the universe works. We might discover particles and forces never seen before, or find that dark energy, the unknown force that accelerates the expansion of the universe, needs to be reconsidered. With each new discovery, our ideas about space have evolved. For example, the cosmic microwave background radiation discovered in 1965 was a strong proof of the Big Bang theory. Before that, scientists thought the universe would last forever, growing at the same rate indefinitely. However, new evidence showed this was not the case. In the late 1990s, when we discovered that the universe was constantly expanding, we also learned about dark energy and its impact on its expansion. Every time we discover something new, we check whether it fits with our previous knowledge and generate new ways of understanding the universe. If it were not for this problem we face, cosmology could lead us to find better ways to understand the universe. Although this problem is complex, it is also exciting because it drives us to develop better tools to explore space. Scientists around the world are interested in this cosmological problem because everyone wants to know more about the universe. Most importantly, this demonstrates how science is always evolving as we learn more about space. Sigma tension is another concept that goes hand in hand with Hubble tension and refers to how matter is distributed in space. We use this information to create a structure of the universe and see how it has changed over time. Some areas of space have many galaxies clustered together, while others do not. Scientists use different methods to determine the magnitude of this dispersion. One possible way to address this is to look at how different densities of matter, such as galaxy clusters, bend light from distant galaxies. This phenomenon, known as gravitational lensing, allows us to see whether the dark matter is, which does not emit light and is therefore undetectable. Scientists also analyze the cosmic microwave background, the CMB radiation, an afterglow from the Big Bang. This light has traveled for about 13.8 billion years, carrying information since the beginning of the universe. By studying the CMB, scientists can understand how the universe was full of irregularities when it formed. However, there is a problem. This data does not match the large-scale irregularities observed in the current universe. The non-spherical distribution of gravity suggests that matter in the early universe was more uniform than seen with gravitational lensing. This suggests that there is something we are not considering in our interpretation, which brings us back to the idea of dark matter and how it works. According to Rees, he and his team were able to redefine their work thanks to the Webb Space Telescope and wanted to find out if a possible error in the Hubble Space Telescope measurements could be the cause of this discrepancy. However, the JWST showed the same deviations, which is worrying. Somewhere between these two observations, there must be a fundamental flaw in our understanding of the universe, Rees said in an interview with an astronomical magazine in the United States. Using the new space telescope has allowed us to look deeper into the universe through its sharp infrared view and study cosmic distances with ever more precision. Both dark matter and dark energy are enigmatic components that make up a significant part of the universe, but their nature remains elusive. While black holes have been the leading explanation for certain gravitational effects, there is growing interest in exploring how dark matter and dark energy could influence this cosmic phenomena. The more we investigate dark matter, the more elusive it becomes. Unlike normal matter, dark matter does not emit, absorb, or reflect light. Its presence is only inferred through gravitational effects. Galaxy rotation curves, for example, show stars on the outer edges moving faster than expected, something that contradicts Newtonian mechanics unless an invisible form of mass is providing the gravitational pull. Simulations of large-scale structure formation also only make sense if dark matter is included. Without it, the universe's current distribution of galaxies, filaments, and voids cannot be explained. The question remains, what is dark matter actually made of? Several candidates have been proposed, including weakly interacting massive particles, WIMPs, actions, and sterile neutrinos. WIMPs, once the most popular theory, are hypothetical particles that interact via gravity and possibly the weak nuclear force. Yet after decades of direct detection efforts using massive underground detectors shielded from cosmic rays, no conclusive WIMP evidence has emerged. Meanwhile, actions, ultralight particles that might solve other mysteries in particle physics, have not yet been found, despite several ambitious experiments. As a result, the scientific community has begun to explore more exotic explanations, including the possibility that dark matter is not a particle at all, but a modification of gravity at large scales. Dark energy, on the other hand, poses a different challenge. It is not a pull, but a push, a mysterious repulsive force that accelerates the expansion of the universe. In 1998, two independent teams studying distant Type Ia supernovae found that the expansion rate was increasing, not slowing down. This discovery earned them the Nobel Prize and introduced a new parameter into Einstein's equations, the cosmological constant, often denoted as lambda. Yet the nature of this constant remains unknown. Some theorists suggest it is the energy of empty space, vacuum energy, while others argue it might be the result of a dynamic field dubbed quintessence that evolves over time. The James Webb Space Telescope's sharp resolution and ability to observe infrared light have now allowed cosmologists to examine the structures of galaxies and clusters at unprecedented depths, and to test competing models of dark energy. For instance, one recent image captured Webb's view of a remote galaxy whose shape and gravitational lensing pattern suggested a stronger-than-expected presence of dark matter, and possibly an interaction between dark matter and dark energy. While these findings remain preliminary, they may hint that the two phenomena are not entirely independent but part of a larger unified framework. Beyond the quest for dark matter and dark energy, the James Webb Space Telescope has begun to offer insights into the very first stars and galaxies. Known as Population 3 stars, these hypothetical early stars formed from primordial hydrogen and helium, before heavier elements, known as metals in astronomical terms, had been forged in stellar cores. The existence of such stars has long been theorized, but no definitive observation has ever been made, until now. Webb's infrared instruments may have captured the spectral signatures of galaxies that date back to within 300 million years after the Big Bang. The light from these galaxies appears devoid of metal lines, hinting at the presence of truly ancient stars. Such discoveries challenge our understanding of how quickly galaxies formed and how the early universe transitioned from a dark, neutral state into the hot, ionized cosmos we observe today, a period known as the epoch of reionization. Previously, it was thought this transformation took hundreds of millions of years, driven by the radiation from young stars and black holes. But Webb's detection of strong Lyman alpha emission lines in these galaxies implies the reionization may have happened more quickly or through a different mechanism than anticipated. Once again, the standard cosmological model is being tested and stretched, to accommodate the unexpected. At the heart of these inquiries lies the so-called cosmic tension or Hubble tension, the discrepancy between different measurements of the universe's expansion rate. When we measure the Hubble constant using local methods, such as observing Cepheid variables or supernovae, we get a value around 73 to 74 km per second per megaparsec. When using early universe data like the CMB, we arrive at a lower figure, around 67 to 68. The James Webb Space Telescope was expected to serve as an impartial judge, refining both measurements through new precision observations. However, the tension has not only persisted, it has widened. As Nobel laureate Adam Rees explained, this disagreement may indicate that we're missing a key element in our model of cosmology. Perhaps a new type of neutrino exists, what some theorists call a dark radiation particle. Or perhaps gravity itself behaves differently on cosmic scales than Einstein's general relativity predicts. Some scientists have even proposed that the universe underwent an early phase transition, a brief but violent change in its fundamental properties, that altered how structure and expansion evolved. Webb, with its capacity to peer deep into both time and space, may help resolve which of these exotic possibilities holds weight. Equally captivating is the telescope's ability to explore galactic evolution across billions of years. Images taken from Webb show that some of the earliest galaxies were surprisingly mature, featuring well-defined spiral arms, disk structures, and even signs of central supermassive black holes. This defies the traditional belief that early galaxies were chaotic, clumpy collections of stars. How could such structure have emerged so soon after the Big Bang? Were the conditions for star formation more efficient in the early universe, or does this point to a fundamental revision in our understanding of cosmic timelines? Moreover, the gravitational lensing offered by massive clusters, like Pandora's cluster and the Hubble frontier fields, has enabled Webb to magnify and study galaxies too distant to otherwise detect. These gravitational lenses act as natural cosmic telescopes, bending light and amplifying the faintest glows of primordial matter. Some of these galaxies appear so old and so large that they shouldn't exist under the lambda-CDM model, the standard model of cosmology. Once again, the tools of observation are forcing us to rethink the very theories they were meant to support. Scientists are now considering new cosmological models that incorporate additional dimensions, modified gravity, or dynamic vacuum energy. Others are exploring quantum gravity frameworks, such as loop quantum cosmology, which suggests that the universe may have undergone a bounce rather than a singular Big Bang. In such models, our current expanding universe might be just one phase of a larger cyclic reality, perhaps preceded by a contracting universe that came before. The detection of certain signatures, like primordial gravitational waves or non-Gaussian fluctuations in the CMB, could lend support to such radical ideas. All of this underscores a deeper truth. Science is a dynamic process. As our instruments improve and our observations deepen, we must be willing to adapt our theories to match the data, not the other way around. The James Webb Space Telescope represents not just a technological leap, but a philosophical challenge. It confronts us with beauty and strangeness in equal measure, urging us to look beyond what. If the CMB was the whisper of the early universe, then Webb's infrared gaze is the echo of its dreams, complex, layered, and filled with unexpected harmonies. We are, as Carl Sagan once said, a way for the cosmos to know itself. But perhaps the cosmos is stranger than we dare to imagine, more dynamic, more interactive, and more conscious of its observers than we once believed. As we move forward, the biggest breakthroughs may not come from confirming our models, but from disproving them. When data doesn't fit, it points to something new, some principle, force, or structure we've yet to grasp. In that sense, the discrepancies themselves are not failures but signs of progress. They remind us that the universe is not obligated to fit our expectations. The journey from Galileo's telescope to Hubble's lens to Webb's mirror is one of expanding vision, both literally and metaphorically. Each new observatory opens a wider window, showing us that the cosmos is not just vast, but alive with mystery. And in that mystery lies the promise of deeper understanding, not only of stars and galaxies but of time, origin, and perhaps even purpose. In closing, we stand at a threshold. The questions posed by the James Webb Space Telescope, about dark matter, dark energy, cosmic tension, and the very architecture of space-time, are not merely academic. They touch on the deepest aspects of human inquiry. Where did we come from? Why does the universe behave the way it does? Are we alone? And is the fabric of reality more complex than we've ever dared to conceive? With every new observation, Webb compels us to reconsider the answer. And in doing so, it not only changes what we know, it changes who we are.